Hello students, this is lecture 12 of MTH 201. In the last lecture, we discussed gradient and directional derivative of a function. So today let us talk about tangent plane to a surface. So let S be a surface in R3 and let R0 be a point in S. If there is a plane which contains the tangent lines at R0 to all the curves in S passing through the point R0, then this plane is called the tangent plane to S at R0. So remember that such a plane need not exist, like for a function of one variable, you may not always have a tangent line, right? For example, if the graph of the function has a corner, then you know that there is no tangent line. So similar thing can happen here as well. So if such a plane, if there is a plane, then that plane is called a tangent plane. Okay. A normal to the tangent plane is often said to be perpendicular to S. Okay. So if you have a tangent plane at the point, let's say R0, then the normal to that vector is said to be perpendicular to S at the point R0. So now we are going to talk about in the next slide tangent plane to a level surface. Okay. So suppose the surface S that you see in the picture is a level surface of some function f. Okay. So S is level surface of a function f. Now you take this curve CT on the surface passing through the point R0. Okay. So this is the point R0 through which this curve CT passes. Now, what do we know about the tangent line to this curve? So this is the tangent vector which is C prime T naught if C of T naught is R naught. So this is C prime T naught. So you will have a tangent plane which contains this vector, right? Because tangent plane, you know, is the collection of all the tangent lines to all the curves at this point, right? So now we will show that the gradient of the function at this point is actually perpendicular to this tangent vector. Okay. Now this is one of the curves, right? CT is one of the curves. If you take any other curve, then again we will show that this is perpendicular to the tangent vector to any other curve. So what will happen is this gradient f at R0 turns out to be the normal to the tangent plane at the point R0 if you have a level surface. So that need not be true all the time. This is the case when S is a level surface. So let us look at the next slide. So let f going from R3 to R be a differentiable function and let b be a scalar. Let R0 lies on the level surface S which is given by f of x, y, z equal to b. Okay, so you have a point on the level surface and suppose the gradient at that point exists and is non-zero. So this is a requirement that you will see will be used. So this is a requirement for the existence of a well-defined plane to the surface S at the point R0. Okay, so the gradient exists and is non-zero at that point. Remember, gradient is a vector. So we are saying this vector is non-zero, meaning there is at least one entry in the vector, at least one component which is non-zero. Now, let CT be a differentiable curve on S which passes through R0. So keep the picture on the previous slide in the background so that you understand what is written here. So let CT be any differentiable curve on S passing through the point R0 and let C of T0 be equal to R0. So C takes the value R0 at the point T0. then f of ct is equal to b for all t. Why? Because the curve ct lies on s and s is a level surface. That means that the entire curve should be on the level surface. Therefore, f of any point on the curve should be equal to b. Therefore, if we use chain rule and differentiate this, we get gradient of fct dot with c prime t. This should have been c prime t. So gradient of f at ct dot c prime t should be 0 for all t. In particular, if I put t equal to t naught, then gradient of f, what is ct naught? It's r naught dot with c prime t naught. I'm sorry, this should have been c prime t naught. So this is 0. Thus, the gradient of f at the point r naught is perpendicular to the tangent vector c prime t naught of any curve ct on S with c of t naught equal to r naught. Okay. Therefore, gradient of f at r naught is normal to the tangent plane to S at r naught because ct is any arbitrary curve. So, so if I put in the values for the point r naught, so let's say r naught is x naught, y naught, z naught, then what is the equation of the tangent plane? Because the normal is gradient. So what is gradient of f at r naught? It's the partial derivative of f with respect to x at r naught, comma partial derivative of y f with respect to y at r naught, comma partial derivative of z f with respect to z at r naught. So when you put in the normal vector and you compute the equation of the tangent plane, this is what you get. So this equation you have seen earlier, right? This is the equation of the tangent plane passing through the point x naught, y naught, z naught with normal gradient f r naught. So this is the equation of the tangent plane at a point to a level surface. Now, if you have a level curve which is an R2, then you drop the third entry, right? Then you just have two terms here. Okay. Let us look at this example. Find the equation of the tangent plane to the surface x square plus 2y square plus 3z square equal to 10 at the point 1 square root 3 1. So whatever point is given to you must lie on this surface, right? Otherwise, there's no point in talking about tangent plane to the surface at that point, right? Unless the point lies on it. So with a quick substitution, so if you put x equal to 1, y equal to square root 3 and z equal to 1, you can see that this equation will be satisfied. Now what is this an equation of? It's an ellipsoid, right? So we are talking about a particular kind of surface which is actually ellipsoid, and we are talking about tangent plane to that ellipsoid at this point. So what are the key ingredients for a tangent plane? You just need to compute the gradient, right? So this is the function f that is given to you. What is the gradient of f? It's 2x, 4y, 6z, which is the partial derivatives of f with respect to the three variables. So the normal to the tangent plane at the point r0, which is this point, is nothing but gradient evaluated at this point, which gives you this quantity, this vector. So the equation of the tangent plane at this point with this normal is given by this, which can be written as this. Okay. So this is how one computes equation of a tangent plane to a level surface. Okay. So in the next few slides, we are going to talk about what is known as implicit differentiation. It's you have seen a version of it in one variable, right? When you use to implicitly differentiate an equation with respect to one variable. So let f go goes from R to R be a differentiable function. And let capital F from R2 to R be a differentiable function. So you have two functions, one which is one variable function, other is a two variable function but taking scalar values. Now let y equal to fx satisfies the relation capital F xy is 0. What do you mean by it satisfies this relation? Meaning if I substitute y in place of y fx, then this equation is satisfied, which means capital F of x comma fx is 0. So let us focus on this f of x comma fx equal to 0 and use chain rule and differentiate with respect to x. So what do we get? By chain rule we know that derivative would be, I'm sorry, this should have been fx. So you differentiate f with respect to x comma fx plus differentiate f with respect to y x comma fx, but at the y-th coordinate you have fx, so you will have an extra term which is the derivative term that will be equal to 0. Therefore if fy of x comma fx is non-zero, then f prime x would become minus of fx x comma fx. Remember, this is f sub x, this is f sub x. Okay, fx x comma fx divided by fy x comma fx if this term is non-zero. Okay, right? So remember this these steps. So what I'm saying is that if you can write y in terms of x, then this is the relationship. Okay. So the condition fy, that condition, last condition that we saw, that it's non-zero at this point, is crucial. So let us see this example. The question is, can y be expressed as a function of x, that is y equal to fx, such that x comma fx satisfies the equation x minus y to the 5 equal to 0. Okay, so here what is capital F of x comma y? It's x minus y to the 5, right? So if we compute the partial derivatives with respect to x, you get 1, with respect to y you get minus 5y square. So here it's easy to see that if I take y equal to fx equal to x to the 1 by 5, this would be the only function that satisfies this equation, right? Why? Because what is this equation? This equation means that x minus fx to the power 5 is 0, which means that fx has no option but to be x to the 1 by 5, right? This is the only possible function. But this function is not differentiable at x equal to 0, right? Why is it not differentiable? Because if you compute the slope, it comes out to be infinite. And note that fy is 0 at all the points on this with y equal to 0, right? So when is fy 0? When minus 5y square is 0, meaning y is 0. But that also means x is 0. So when you look at the graph of this function, right, the level curve basically of this function at 0, then you see a problem, right? You don't have differentiability. So this is the graph of the function. So at the point 0, 0, you have this, right? Okay. So when you look at this function, there you have to avoid this point, right? Because this point is, at this point it's not differentiable. Okay. All right. Let us look at another example. The condition fy is crucial. So let us first try to understand this example through a picture and then we will look at So you have this circle. This circle is a unit circle. So what is the equation of a unit circle? X square plus y square equal to 1, right? Okay. So now when you look at these points minus 1 comma 0 and 1 comma 0 and you look at the tangent line, it's vertical, right? That means there's a problem. You don't have a finite slope. And what happens around this? So what is the equation of this circle? X square plus y square equal to 1. So if you want to write y as a function of x, there are two options. One is plus of square root 1 minus x square. Other is minus of square root 1 minus x square. Right? So if I am at this point 1 comma 0, then around this point, this function there'll be two definitions, right? On the top, the definition will be square root 1 minus x square. On the bottom, your definition would be minus square root 1 minus x square. So you don't have a well-defined function which is differentiable around this point, right? Such that y is a function of x. And similar thing happens around the point minus 1 comma 0. Whereas if you take any point which is in the uh, positive y-axis direction, let's say this green point x comma y, then you can define y equal to plus square root 1 minus x square locally, right? In a neighborhood, in a small region around this point, you can define y as a function of x, which is differentiable. Similarly, if you take this bottom part and you take any point, let's say this violet point x comma y, then you can write y as minus of square root 1 minus x square around this point, right? So there are only two problem points on this entire unit circle, which is 1 comma 0 and minus 1 comma 0. Other than that, in a small region about any given point of type green or purple, you can write y as a function of x, which is differentiable. So let us, we just spoke in words, but let us, using the picture, but let us formally write it down. So the question is, can y be expressed as a function of x, that is y equal to fx, such that x comma fx satisfies this equation, right? Here, what is capital F? It's x square plus y square minus 1, because the equation is capital Fxy equal to 0. So what are the partial derivatives? It's 2x and 2y. At what points is Fy 0? When y is 0, right? But when y is 0, you substitute y equal to 0 here, you get x square equal to 1, which is x is plus minus 1, which are these 2 points, 1 comma 0 and minus 1 comma 0. So near 1 comma 0, the unit circle cannot be described as graph of a function y equal to fx, since for each value of x close to 1, there will be two values of y, right? One is plus square root 1 minus x square, other is minus square root 1 minus x square. Similarly, near minus 1 comma 0, right? Near points other than these 2 points, if you are on the top side, which is y greater than 0, then your function is plus square root 1 minus x square. If you are below the x-axis, which is y less than 0, then you have function to be minus of square root 1 minus x square. So here you have legitimate functions, whereas you don't have legitimate functions near 1 comma 0 and minus 1 comma 0. It's important to note here that a point x comma y with y non-zero satisfies x square plus y square equal to 1 only if the term 1 minus x square inside the square root is positive, right? Because if y is non-zero, right, then 1 minus y square should be greater than or equal to 0 because you have x square term. Or alternately, if you bring x square on the right, you get y square equal to 1 minus x square. Because y square is non-negative or positive, 1 minus x square should be positive. But when is 1 minus x square positive? 1 minus x square is positive when x lies between minus 1 and 1. And these square roots are also defined then, right? So there's no problem that's happening here because you are on this curve. These terms are well defined. Okay, terms inside the square root is positive. Okay, so when you're reading this slide, keep the previous picture, the picture on the previous slide in mind, and that will make you understand what's going on. Okay, so it turns out from these two examples that the condition that we had imposed, that the partial derivative of f with respect to y is non-zero, is going to be crucial, and that's basically the case. Okay, so let us look at implicit function theorem statement in R2. We are not going to prove it, we are just going to state it. So let capital F from R2 to R be a continuously differentiable function. What is a continuously differentiable function? A function which is differentiable and the partial derivatives, the first order partial derivatives, are continuous. We have seen this definition before. Suppose you have a point x0, y0 in R2 such that the partial derivative of f with respect to y at this point is non-zero. Then in some disk about this point, so in a closed region around this point, the set of points x comma y which satisfy this equation is the graph of a function y equal to fx. Okay, so you indeed get a graph of the curve can be written as graph of a function y equal to fx if your partial derivative with respect to y is non-zero. And from the previous discussion, what should be the derivative? If y equal to fx is, when we put it in this equation, satisfied, then f prime x should be negative of fx, x comma fx divided by fy, x comma fx, and this holds in the entire disk. Okay. Note that the disk is such that all the points x comma y in the disk satisfying fxy equal to 0 and the partial derivative with respect to y non-zero. And there is such a disk about x0, y0. Why? Because if at the point x0, y0, fy is non-zero, then there should be a region around, there should be a disk around x0, y0 where it stays non-zero because it's a continuous function, right? So a continuous function, if it's non-zero at a point, then in some disk around that point, it remains non-zero. So this will be a homework part of the problem set. Okay, proving that a function which is continuous is non-zero at a point, then it remains non-zero near that point. We have seen such a result in one variable, but that also holds true in more than one variable. Okay, so you need continuity of the partial derivative. Therefore, we have written continuously differentiable. We needed this part. Okay. In R3, you can extend this. So if you have a function capital F from R3 to R, and suppose you have a level surface f of x comma y comma z is 0, and suppose you have a point on this surface such that the partial derivative of f with respect to z at this point is non-zero. then in some ball about this point, the surface can be described as graph of a function. So see there f sub y or partial derivative with respect to y was non-zero. So we could write y as a function of x. Now partial derivative of f with respect to z is non-zero. So we can write z as a function of remaining variables. What are the remaining variables here? X and y. So you can write the surface as graph of a function z equal to fxy. Okay. In some ball about this point where the partial derivative is non-zero. And note that z naught is equal to f of x naught y naught. Why? Because in a small ball about this point, you can describe it as a graph. That means this point should also be satisfied by this equation, right? Okay, so therefore z naught is f of x naught y naught. Now, because this is satisfied, right? When you put z equal to fxy in the equation fxyz equal to 0, it satisfies that curve. Therefore, you have this equation. So, if you differentiate with respect to x, this equation you get where do x appear in the first entry and the third entry, right? So, by chain rule, you will have fx, x comma y comma fxy plus fz, x comma y comma fxy times chain rule, right? So partial derivative of f with respect to x at this point should be 0. And if you differentiate with respect to y, where does y appear? In the second and the third place, right? So you get f sub y, x comma y comma fxy plus you differentiate f with respect to the third variable, which is fz at this point, times the partial derivative of f with respect to y. This is differentiating with respect to y. So if you put this together, okay, so what I'll do is, because fz is non-zero, here also fz is non-zero, so you can take out fx, right? So fx would be minus of capital Fx divided by fz. So fx, I'm writing it in matrix form because if I look at this matrix, this is nothing but the Jacobian matrix of f. But f sub x from the first equation is minus capital Fx by capital Fz, and f sub y is from the second equation minus f sub y by fz, right? So this is the derivative matrix. And like the previous note, the balls is such that the points in the ball lying on this surface fz is non-zero, and there is such a ball because again fz is continuous. So if you have a continuous function which is non-zero at a point, then there is a disk about that point where it remains non-zero. Okay, so let us look at a few examples that will make things clear. So let capital F be this: near what points the level surface capital F x y z equal to 0 can be described as the graph of a differentiable function. So from implicit function theorem, we know that uh, you can write z as a function of x and y provided capital F with respect to the partial derivative of capital X f with respect to z is non-zero, right? So let us compute that. So what is the partial derivative of f with respect to z? Z only appears in the first term, so you get 2x cube z. When is this 0? This is 0 when either x or z is 0, right? So this is 0 if and only if xz is 0. Hence, by the implicit function theorem, the level surface f can be described as the graph of a differentiable function z near the points x, y, z which satisfy this level surface, and xz is non-zero, right? Because xz non-zero is a requirement for implicit function theorem. So, what should be z? Now, it's easy to compute z from here, right? Because if this is 0, then z comes out to be 4 minus xy square divided by x cube square root, right? So when z is positive, see z can't be 0 because if z is 0, then fz is 0. So you are only looking at z's which are non-zero. So if z is non-zero, then z can either be positive or negative. So near the points when z is positive, this is the definition, positive square root. And if z is negative, then you have negative square root. Okay. And it's also again important to note here that a point which x z non-zero satisfies this equation only if this term is positive, right? Because z square equal to f4 minus xy square by x cube. So z square is positive, therefore this term has to be positive. Right? So these are legitimate functions, but they only work near z positive. Because once z hits 0, then your fz becomes 0 and then implicit function theorem does not give you anything. Right? Okay. So now let us look at another example. So prove that x cube minus sine y plus y to the 4 plus 7 equal to 8 defines y equal to fx as a function of x near the point 1 comma 0 and calculate the derivative at that point. So here what is capital F? Capital F is this, right? You so the equation should be of the type fxy equal to 0, right? So you bring in this 8 on the left, so that equation looks like fxy equal to 0, and then fxy is equal to x cube minus sine y plus y to the 4 minus 1. Okay. So the given curve is the level curve C given by fxy equal to 0, and 1 comma 0 is there on this level surface, which is important. Now what is fy? Because we want to write y as a function of x, so we have to compute partial with respect to y, which comes out to be minus cos y plus y cube, right? So now we want to apply implicit function theorem near the point 1 comma 0. So if I substitute this point 1 comma 0, then what happens? There is no x term, so you put y equal to 0. If you put y equal to 0, you get minus cos 0, which is minus 1, which is non-zero. So implicit function theorem makes sense. Thus, by the implicit function theorem, near the point 1 comma 0, the curve can be described as the graph of a differentiable function y equal to fx. And this example is interesting since at the face of it, one cannot predict the existence of such a function, right? You cannot immediately see that you can write y as a function of x, right? In the previous example, you were able to do that. Even in the circle example, you were able to write y as a function of x, but not here. Here it's not immediate. But implicit function theorem guarantees that there has to be such a function at this point. What is f prime 1? By the result, it is minus of fx at the point divided by fy at the point. It's not difficult to remember this expression because what comes in the denominator is what is non-zero, right? Which is f sub y. And then there should be a negative sign, and in the numerator you should have fx. So it's just a simple computation now. You've already computed f sub y at the point. You just need to compute f sub x. F sub x here is 3x cube. At the given point it comes out to be 3, and therefore you get minus 3 by minus 1, which is 3. So f prime 1 comes out to be 3. Let us finally look at one more example. So prove that sine of xz minus 2yz is 0. Okay. We want to show that there is a function, differentiable function f, such that z equal to fxy satisfies this near this point. And you have to calculate the partial derivative of little f with respect to x and y at this point. So here your fxy is given by this, and the given surface is the level surface S given by this function, and the given point lies on this, right, which is important. What is fz? Because you want to write z as a function of x and y, therefore you compute partial of f with respect to z. You can just differentiate this, you get that. You evaluate fz at the given point, you get -3, which is non-zero. Therefore, by the implicit function theorem, near the given point, the surface can be described as the graph of a differentiable function. Again, this example um, is interesting because it's not immediate that you can write z as a function of x and y, right? But implicit function theorem guarantees that. Okay. And what is fx? Fx is minus f sub x divided by f sub z. And fx you can compute as this. You evaluate at the point, you get 0. Therefore, fx is 0. And this is a strange example where both fx and fy are 0 at this point. Okay, so this is also 0. So this is what you get. Okay, so let us stop here.